Good morning. Morning. Okay. Well, it's very good to be here, and it's good to see many of my Haitian friends here in this session. This session is focusing on Haiti and the aftermath of the January 12th earthquake. My name is Yvonne Chikata, and I'm the country director for the Caribbean, which includes Haiti. Before we get into the main session, we have many of our friends from Haiti here, and there's one in particular that I would like to invite to say very few words. Yolene Surena is known to anyone who works on Haiti. I think it's fair to say you could call her the mother of civil protection in Haiti. And we've asked her to come and say a few words to get us started this morning. Yolene.
Thank you, Yvonne. Thank you, everyone. It's a great pleasure for me to be with you this morning for this important session and have the opportunity to greet you in the name of the all Haitian people. Before the earthquake, we have a few scientific knowledge about all of the hazard that we are facing. The challenge for us is right now to have the opportunity to get advantages from all of that knowledge that was developed in the last 4 months. We have to go further. We have to take advantage of all of that opportunity that we are receiving right now. And I think that not only from the document that they are going to present to you, but also from the discussion, Haiti has a lot of things to get from it. The civil protection is very weak right now. We have to train people. That will take time to train them, to give them the ability to use all of that knowledge. But I'm sure with the support of all of you, and with your support, Yvonne, because we know that how much you get Haiti in your heart, and with the support of all of the projects that the World Bank has in Haiti, we can go further and have a good success. Thank you very much, and have a great day.
Thank you very much, Elaine. Let us now get started. A couple of housekeeping items and a little bit of a sense of how we expect this to unfold. We're going to have 3 groups. They will speak sequentially. We expect them to speak each for about 20 minutes, and then we'll open it up for about half an hour for your questions, tweets, etc. If you do have questions, please write them on the pads that were in the package that you received, your welcome package, and hand it to an usher, and that way we can make sure that your question gets up and that it gets answered. So I am going to, you have the full bios of all the speakers for these sessions, but I'm going to first ask the first group to come up. And they are really going to focus on what happened, the links between the seismic activity and the earthquake, etc. And Carol Prentice from USGS will lead that off. The second group is going to talk a little bit about the kinds of interesting new technology and approaches that were used in the aftermath of the earthquake, including the remote sensing for the damage assessment. And then the third group is going to really talk about the way forward. We know that we need to integrate this kind of technology and this kind of risk dimension in the reconstruction effort. And they'll talk a little bit about what kinds of efforts are underway to do this multi-hazard assessment. So without much further ado, I'm going to ask Carol and her team to come up. Thank you.
Good morning. Thank you for coming to our session on the Haiti earthquake. I hope we have a presentation here. Well, my job this morning is really to set the stage, to give you some basic information about the Haiti earthquake and also about the Caribbean region in general. And if we can ever get the slides up. Oh, goodness. the main point that I'd like to leave you with is that earthquakes of this size are inevitable. Future earthquakes will occur in Haiti, and they're inevitable really throughout the Caribbean region. It's a good thing you came up here. So the earthquake of January 12th, 2010, was a magnitude 7 earthquake.
I apologize for this. This should not have been closed, but it will be opened momentarily. Okay, is this you right here? This one?
Yeah.
All right.
Okay, I get to start my time now, right?
Yes, you do.
Okay, great. And let's just move right on. Okay, so again, I'm going to talk about this earthquake, give you a regional overview, and hopefully leave you with this notion that future large earthquakes are inevitable. This is a map showing most of the island of Hispaniola, which is shared by Haiti on the west, Dominican Republic on the east. And it shows an estimate of the intensity of shaking. The red colors are the most intense ground shaking, and that corresponds also with the highest concentration of population near Port-au-Prince. But the whole island felt the shaking. Indeed, the whole region felt the shaking. The earthquake was a magnitude 7, happened Tuesday afternoon just before 5 o'clock, with the epicenter about 25 kilometers southwest of Port-au-Prince. Depth of the earthquake was about 13 kilometers. The duration of shaking, something like 30 seconds. It's important to recognize that there was no seismic network in Haiti at the time, so we do have some significant gaps in our understanding of this earthquake due to that fact. No strong motion instruments in Port-au-Prince to tell us much about the actual ground motion. This shows the aftershocks that occurred within the first few days after the earthquake. The most important thing to note here is that the aftershocks are really concentrated out to the west, and that tells us that that's the part of the fault that produced this earthquake, was from the epicenter out to the west dominantly. Okay, the consequences of the earthquake, horrendous. They left over 230,000 people dead, over 1 million people homeless. Out of a population of about 9 million in Haiti, over 3 million were affected by this earthquake. There was damage, significant damage from liquefaction in the port area. There were some deaths due to local small tsunamis, but by and large, by far, most of the casualties were the result of building collapses, such as you see in these photographs. It's important to realize that the earthquake was a natural phenomenon, but as we see in so many places in the world, the catastrophe is largely man-made. I wanted to put the earthquake into some perspective for you. This is a plot compiled by Roger Billum at the University of Colorado, showing earthquake magnitude on the horizontal axis, deaths per earthquake on the vertical axis, and note where Haiti, which is the red dot, lies on this plot. It is the largest, has caused more deaths than any other magnitude 7. These are all compiled since 1900. In fact, it killed more than twice as many people than any other magnitude 7 earthquake. It's also the fourth most deadly earthquake of any magnitude since 1900. And again, what makes a magnitude 7 earthquake into a catastrophe? The answer is complex, but certainly two of the most important parts of any answer to that question: poor construction and an unprepared population. It's instructive to look at the top 12 killer earthquakes, which are now shown in red. And I note with some horror that of those top 12, 5 have occurred in the last 10 years. Now, that's not because there's been any increase in earthquakes. The Earth is doing the same thing it's always done. It's because we are not paying good attention to our seismic hazard as we develop large cities. Okay, well, I wanted to zoom in on the Haitian Peninsula here. We can see here the Enriquillo Plantain Garden Fault. It's very well expressed in the topography. And I want to take the lines away so you can see again the signature of this fault through the topography. The fault had been identified and mapped by Paul Mann at the time of the earthquake, and we had some GPS geodesy, which Eric Calais will talk about in a few moments, that told us that strain was accumulating at a rate of 7 millimeters a year. So when the earthquake happened, we presumed that this was the fault responsible. And when we looked at our very high resolution imagery, we had great imagery immediately after this earthquake to work with. We could see the evidence for past earthquakes on this fault, and you can see the fault scarp shown by that arrow there. Very clear evidence for recent motion. But when we zoom in, we see absolutely no evidence for surface rupture on this fault associated with this earthquake. Instead, the main geologic signature of this earthquake is coastal uplift. On the left, you have an image showing a happy coral reef just offshore there. On the right, you have a post-earthquake image showing that reef sticking up out of the water. And it was exposed as a result of coastal uplift. The beach was widened. When you go look at that coral reef, this is what you see, happy birds and unhappy corals. The red color in this photograph indicates where the corals are alive. The grays are the corals that were killed as a result of the earthquake. We can measure that difference, and we can document the amount of uplift and the distribution of uplift along the coast, and that's what we did after the earthquake. Putting that together with geodetic information, with seismologic information, we can put together a fault model. You have to rely on models because the fault didn't come to the surface. And the bottom line is that most of the slip that produced this earthquake occurred on a north dipping thrust fault and not on the Enriquillo Plantain Garden Fault. Okay, why should we care about that? Well, we still have the Enriquillo Fault. This earthquake did not release any slip along the fault, and in particular, we have the Enriquillo Fault to the east of the epicenter and close to Port-au-Prince. Remember that most of the slip occurred to the west of the epicenter. We still have this big fault even closer to Port-au-Prince that did not rupture during this earthquake. We know from walking along the fault that there's abundant evidence of past earthquakes. Here's a 23-meter left lateral offset that's the result of numerous earthquakes, probably around 7 to 10 earthquakes. We also see very small offsets. In this case, about 2.5 meters. They range up to about 3.5 meters. And these are most likely the result of the most recent earthquake, not January 12th. We have to go back to the 18th century in order to find the date for this most recent earthquake on this fault. So then the question becomes, and here's the historical seismicity as compiled by Bill McCann. If we haven't had a big earthquake along this fault since the 18th century, the question then becomes how much strain has been accumulated in that time, and Eric Clay will give you an answer to that question.
Good morning. My group has been working in Haiti for a number of years now trying to answer this precise question, how much strain, elastic strain, is building up on these faults, strain to be released in earthquakes to come. We do this in particular using GPS technology, the same technology you may have in your cell phone. And you see two examples of GPS setups in Jacmel and in Port-au-Prince in Haiti. The way we use GPS is quite a bit more involved than what you have in your cell phone. We're able to position our benchmarks with a precision of a millimeter, and we can basically track the motion of the Earth's crust with a precision sufficient to measure the speed at which your fingernails grow. That's pretty much what we have to do to capture what's going on these faults. The way we show our results in terms of the motions of the Earth's crust is by arrows like you see on this picture. And these arrows show the displacement before the earthquake, or over the past 10 years before the earthquake in Hispaniola, the horizontal displacement. And you can see on this map that the island of Hispaniola is being sheared in a kind of horizontal east-west direction at about 2 centimeters per year. It's on the plate boundary that's consistent with that. You can also see that there is a gradient in these arrows with pretty much 0 in the south and all the way up to 20 millimeters in the north. Well, that's the bad news, because this gradient in the displacement or in the velocity means that there is elastic strain building up. And again, this elastic strain has to be released eventually during earthquakes. And we can look at that in a little more detail on this cross-section from south to north of our GPS results. And again, you want to look at the regions where there is a gradient, a change in the velocities we're measuring. And you see on this profile that there are 2 steps. in the data, one that corresponds to the Enriquillo fault and one that corresponds to the septentrional fault. And then you can do a little bit of math. You can measure this offset, and you can see here that for the Enriquillo fault, we have 7 millimeters per year of strain that is building up over time. Now, we know that the last earthquake that released that strain occurred about 250 years ago, more or less. 7 times 250 is 1.8 meters of slip deficit that this fault has built up since the last earthquake. And we know from earthquake scaling laws that 1.8 meters of slip amounts to a magnitude 7.2, which is unfortunately very close to what happened on January 12th. You can do the same calculation for the septentrional fault with 12 millimeters per year in the last earthquake about 150 years ago. It amounts also to 1.8 meters. So again, it's also ready for a 7.2 event. Now, we can also measure the earthquake itself. And what you're looking at here is positions as a function of time for one particular GPS site located very close to the epicenter. You can see the east-west displacement of this site, the vertical position in red, and in black, the north-south displacement, or the latitude if you want. And you can see that from 2004 to 2009, the site is just moving along as the fault zone is building up elastic energy. And suddenly in 2010, everything changes. There's a sudden offset. Oops, sorry. 54 centimeters of motion to the south at that particular site, 35 to the east, and 35 centimeters up. That's about 0.8 meters, 80 centimeters of total displacement at that particular location. Very easy to pick up in the GPS data. You can look at it in map now. This is a map view of the horizontal displacement due to the earthquake as measured with GPS. You can see a fairly complex pattern. You can see a lot of contraction, which was a big surprise. A lot of north-south contraction. You can also see some horizontal shearing motion. I won't go into the details here, but this is very important information to constrain models of what happened during the earthquake, how much slip there was, where the fault was, and how deep that happened. We can also use a technique we call radar interferometry, which I will illustrate briefly here. Radar satellite, ground surface, and this sinusoidal wave here that schematically represents the radar pinging the ground and measuring the distance between itself and the ground surface. So and the satellite will pass over the same area several times, and if there is an earthquake, if there is ground motion between two consecutive passes, then there is an added half wavelengths or quarter wavelengths, as you can see here in blue, and that will be picked up by the radar satellite. Now you can map this, you can plot this on a map with colors. Of course, if there's no change between the two passes, then the map will have uniform colors, no deformation, nothing to see. But if the ground has moved because there has been an earthquake, then you'll see changes in colors, and that's what you see on this map. This is what we call an interferogram. This one was produced by collaborators at University of Miami, and you can see very clearly fringes in those psychedelic colors there. They indicate the area where the ground moved, and we can quantify that a little bit more because we know that each fringe represents 12 centimeters of ground displacement towards a satellite. You can count the fringes. There are about 7 times 12 is about 80 centimeters more or less, so consistent with the coral uplift that Carol was talking about and with a GPS result. So this is very important information that was available pretty quickly after the earthquake. The GPS came a little later. This is these arrows show the horizontal displacement measured with GPS, and we can use that information to quantify where the fault was, what the dip of the fault was, and we know it was a fault dipping to the north with a lot of dip-slip component. That was a surprise, and of course, on top of that, the aftershocks that are continuing all the way until today. I'll finish by showing a couple of slides on where we're headed next. And this is a map here that shows seismic hazard In Hispaniola, this was made in 2001 under an OAS study. And you can see on this map that, and let me say a few things about these maps. These maps include what we know about the seismicity, what we know about earthquakes. They should also include what we know about GPS result that I just presented. This one does not because there were no GPS results back then. The results are shown in peak ground acceleration, and which is a quantity that engineers need when they want to design earthquake-safe structure. And this, let's call it an old map now, predicted for Port-au-Prince an acceleration of 0.16 g, which amounts to an intensity of 6 to 7, and not quite consistent with what we've seen. Certainly, we've redone these maps, and this is work we've done with colleagues at the USGS, Art Frankel. This is how they look today with the new GPS information built in. And we are now at 0.6 G for the Port-au-Prince area. This is just the beginning of what needs to be done at in a much better way. There are lots of approximations in this product here, but this is where we need to be headed with Haitian colleagues. So a few lessons from Haiti to wrap up here. The first lesson, I think, is that science worked. We were able to forecast the magnitude of this event. That's a success in some ways, and it has to be translated into hazard maps in a better way now, but communicating science failed. For a large part because scientists do not know how to communicate science in the right way to decision maker, and I take that for myself particularly, but also because the risk mitigation system was not properly organized and certainly lacked resources. The reconstruction is starting, and it's an opportunity to move forward with sustainable seismic safety built in. In the short term, that's obvious to everyone, but we also have to think in the long term about how we are going to build science in Haiti and how it's going to be communicated, how education will take place. Capacity building, to me, is the key around which all of this revolves. It's not only about building better, but it's really about building better prepared. And the last point is that we cannot do it all for Haiti. We have to train, we have the responsibility, and certainly I take that for myself as a scientist, to train the next generation of Haitian scientists and also help build the risk reduction strategy for Haiti based on sound science that will help the country move forward and make sure that when the next earthquake happens, because it will happen, the damage will be much less. I'll leave it now to Marie-Lou, who will expand this to a couple other regions in the Caribbean.
Okay, thank you, Eric. So we thought it'd be helpful to close with asking the question, are there any other Haiti-type earthquakes lurking in the Caribbean? This is a map of the region. We've been focusing on the island of Hispaniola, but if you move around the plate boundary shown there in black and move to the southern part of the plate boundary in South America, the city of Caracas is indicated with the orange dot there. Caracas is the home to about 6 million residents. This is a view of Caracas there on the right, looking eastward. And right along the coastline, there is a major fault zone. It's the southern boundary of the Caribbean plate, San Sebastian Fault. And we have GPS measurements down there. We take advantage of islands. And just like Eric described, we can measure the strain that's accumulating on the fault. Points in the ground are moving, and that's loading the fault. It stays stuck until it breaks in a big earthquake. It's being loaded at a rate of about 1 centimeter a year. In 1812, there was a huge earthquake that impacted the region, impacted Caracas. In fact, studying that earthquake now, we think it probably was 2 earthquakes that occurred along this main plate boundary fault in very close succession. The one near Caracas was greater than magnitude 7. It killed, the estimates are about 10,000 of the 40,000 people that were living there at the time. And overall, the 2 earthquakes killed about 26,000 people there then. So we can measure how fast the strain is accumulating. It's been 200 years since the last earthquake, so the same simple math that Eric described means we've accumulated 2 meters of slip, which means a magnitude 7 earthquake could happen there tomorrow. There was a magnitude 6.5 in 1967. It left 240 dead. It's a much smaller earthquake, and many fewer people were living in Caracas, probably only about 20% of the people that are there today. So what would happen if that magnitude 7 earthquake occurred tomorrow? Roughly 4 million of the 6 million people living in Caracas live in self-constructed homes on very steep hillsides. And so I think you can imagine that we're talking about a real catastrophe. Now I want to move quickly to Panama. Down there in the corner at the junction of the South American plate, the oceanic plate called the Cocos plate, and the Caribbean plate. And Panama is literally getting squeezed by all of this plate motion. And we can see that in terms of the active faults that have been mapped there. These were mapped by Tom Rockwell and Eldon Gath. This was part of the study for the expansion of the canal. So you can see there are these major faults. Panama City's down in the bottom right-hand part of the picture. And they identified one fault in particular, the Pedro Miguel fault. I've highlighted it there in yellow. It's a horizontal strike-slip fault. It has had 3 big earthquakes in the last 1,600 years, and the most recent event was in 1671. It was greater than magnitude 7, and in fact, conveniently, the Spanish had built a trail shown in the purple dashes, and that was offset nearly 3 meters. So this is a magnitude 7+ earthquake, and from the geologic information, we know that the strain's accumulating at about 0.5 centimeter a year. It's been 340 years since the last earthquake. We've got 1.7 meters of slip that's accumulated, very similar to what Eric described in Haiti. There could be a magnitude 7 tomorrow. And just so you can see here, that's the Panama City, and I don't know how to turn this. And the canal zone's coming out. The fault is just on the other side of the canal zone. And Panama City's home to 1.5 million people, and there are a lot of poor construction there, as well as the modern high-rises. And just in closing, thank you, Carol. There are many earthquakes occurring around the Caribbean plate, and what we're talking about today for Haiti, let's hope we don't have to have the same conversation for another city in the coming years. Thank you.
Thank you very much. If Ronnie Gucci can come up. I think after this very sobering assessment of what happened, it will be good to hear how technology helped in the aftermath. So we're going to have Ron from ImageCat and then Guido Limon from the EU. Thank you. Okay. And please remember to write your questions down. Anyone in an orange T-shirt, like the lady back there is an usher, you can hand her your question.
Hopefully technology will do well here as well.
I think you got the wrong slide.
Oh, I'm sorry.
Sure, I'll give yours and you'll give mine. Let's see, I think this one right here. About second one. Yeah. Okay, very good. Okay, good morning. It is a pleasure for me to be here today. And it's an even greater pleasure for me to share the presentation stage with my good friend and colleague, Guido Limon. What I'm going to do is I'm going to discuss the damage assessment that we all performed after the earthquake. And Guido's going to pick up and discuss what some of the major steps we're taking right now to make sure that we can improve this process for the next set of events. Let's start by acknowledging what I think was an extraordinary collaboration and partnership between the main organizations, the World Bank, GFDRR, the UN's UNITAR UNISAT organization, the EC's JRC, the Joint Research Center, and of course the Haitian government. But a lot of this wouldn't have occurred without the extremely active bench play of the supporting organizations, and many of them are listed right here. Now, one of the reasons why we're so excited about this event is the imagery. You see here an image that transitions or has transitioned from the pre-earthquake to the post-earthquake area imagery. And the amount of detail and the precision and the richness of this data set is unprecedented. And it allowed us to do a lot of things that we haven't been able to do in previous events. The methodology, in my opinion, was truly innovative. I thought we tried a lot of new things, some experiments, and a lot of it worked. Some of the important innovations besides the imagery that I just showed were, for example, there were multiple independent assessments of damage. Now, this is very important because when you're doing these assessments and you're trying to assess the reliability of these determinations, it's always good to have these independent assessments to give you that reliability index. That is, how many people viewed damage in the very same way. And this helps the decision makers make better decisions because they know the spread or margin of uncertainty that might be associated with this analysis. Another very important development, and it may have been mentioned earlier, is crowdsourcing. Crowdsourcing was used in this event in a very, very big way and for the first time to assess damage to a very, very large area. And what resulted was unexpected. A community of about 600 experts from engineering and scientific communities all pitched in from, I think it was over 20 different countries, 60 different universities, private institutions, and nonprofits, all dedicated their time to help do this damage assessment. And I think this is something that really is going to change the way in which we do these assessments. So this was a major accomplishment. The team also spent an enormous amount of time trying to do field surveys and to integrate this information into our area assessments in order for us to provide a much fuller, richer perspective of damage. Because if you think about it, things that you see from the sky, you can see very well overhead. But if you don't see the sides of these buildings, you really don't get the full picture of damage. And so you need oblique imagery, which is we have that. As well as field inspection teams that were doing sampling in very strategic areas that would allow us to integrate that information into our final damage assessment. So that was an important contribution of our study. Oops. And then also loss modeling techniques. This was another important activity. This is where we use loss estimation modeling in a way to do the extrapolations of damage to lower damage states, the states that we couldn't see from the aerial imagery. So the combination of pulling all these different technologies, I think, really resulted in the most robust data set for this event. Now, we were very, very lucky to have access to so many different data sets. The satellite companies came out very quickly with their data. GOI, Digital Globe were very important partners for all of this. And then later on, the aerial companies, specifically the World Bank, ImageCat, and RIT Remote Sensing Mission, provided very high-resolution aerial imagery along with Google and NOAA. And in addition, there were some other data sets that were unique and new that really provided us a different view of this event, such as the LiDAR that you see there, which provided a three-dimensional picture, essentially, of the earthquake. So this information was very valuable in allowing us to view this earthquake from many, many different perspectives. Okay, so let's look at some of the results here. The first thing I'd like to show you is the distribution of damaged buildings. What we used was a very common scale, damage scale called the EMS 98 scale that allows us to describe damage in terms of performance. So that if you look at this area right here, this is grade 5, and this would be those buildings that were destroyed or had very severe damage. And there were about 10,000 of those buildings. There were about 15,000 buildings that we would classify as grade 4, which would be very heavy damage. There would be about 12,000 that would be severe damage, and then there were about 70,000 that had either moderate or very light damage. But there were a lot of buildings that were affected. The important point here is that if there was damage that had occurred during the event, there was a high propensity for it to be in the very, very high damage states that would probably require rebuilding and not repair. Okay, what did the distribution of damage look like in terms of land use? Well, most of the damage occurred in residential construction, which is not unusual, right? Most of the buildings that you have in urban areas are residential structures, and in most cases, 90% of your building stock would be residential structures. So in terms of percentage, it's not unexpected to see such high percentages there. Okay, here's a table that looks sort of complex, but it's not really. It's slicing and dicing another index that we use to estimate loss. So the numbers in this table here reflect the floor area that either was damaged or might have to be replaced as a function of the damage grade and also by land use. Now, why do we want floor area? Well, in order for us to estimate what the rebuilding costs are, we need to know how much of the building needs to be replaced or repaired, and we were able to use the crowdsourcing technique to get a lot of this information. Now, for Port-au-Prince, the total floor area, if you were to add all this up, it would be about 12 million square meters. And that's, in comparison, that's equivalent to, I think it was 1,200 White Houses. If you were to rebuild the White House 12,000 or 1,200 times, that would be the equivalent of that number right there. The loss was, by all relative standards, was enormous, $2.2 billion, which is about a third of Haiti's gross domestic product. So it's a very large number in terms of their financials. Okay, so the bottom line for all buildings, okay, what I showed was for Port-au-Prince, for all buildings, the total number of buildings that experienced some level of damage was about 300,000 buildings. So this would include Port-au-Prince and the areas that are outlining Port-au-Prince. And out of that 300,000, 30% experience very severe damage, and these buildings will probably have to be replaced and are not repairable. In terms of square footage or floor area, 40 billion square meters, which equates to about $6.4 billion in building damage, which is about 100% of their GDP. And then there's sort of a word of cautionary. What I was describing was building damage, but there was damage to infrastructure, roadways, other things, including social costs that would make this loss even larger, and at some point need to be integrated into these figures. So I'm going to end here. I've got a little quote that I saw on the plane, and it was, "Passion is short-term, love is long-term." And I really think that we need to look at Haiti from the very, very long term in terms of its rebuilding. I've got two quick announcements before I bring Guido up. One is that there's been a lot of reports and data that have been produced under this joint World Bank, UNISTAT, and JRC project, which are available from many sources. And if you're interested in getting any of this information, you can talk to Guido, myself, or Stu Gill at the World Bank. And then also, July 8th, here in Washington, D.C., there's also going to be a workshop sponsored by the National Academies that deals with remote sensing and how it can be used to look at assets and loss and so forth. And I encourage you to pick up one of these flyers that are outside the table there, and we would welcome your attendance there. So I'm going to end right here with Guido bouncing in.
I think I have to escape this one. Okay. So, as Ron already explained, we have the second part more looking into the, say, the lessons learned. We are, say, based on this experience that we have gathered in this particular event, we're looking at ways on how to consolidate this experience and bring it forward in other contexts as well. So, and we're looking specifically at this, say, the experience in what we call the geospatial community, so the people that are typically involved in using remote sensing data, geospatial data to try to do assessments. People are also working in disaster response context. So all of these are very much interested in looking at this rather unique experience. And it's actually, as Ron explained, unique in two ways. Data-wise, so it has been, we have seen huge volumes of very specific high-quality information that was made available, and available in ways that are very unconventional. For instance, they were becoming available directly, very fast, and also directly in the public domain, something we don't see very often. But also, again, this effort, the collaboration that existed, both organized and spontaneous, and how they have contributed to this disaster impact assessment. Plus that we have also collected lots of reference data, also quite unique because many of us are used to looking from this satellite perspective, or at least from a vertical view. We have realized that in fact, the information that comes from the ground, it comes from other sources of information, is actually very important to test our accuracies, to have a good understanding of where our omissions, our errors are, and of course to translate this into this statistical significant cost estimate. So in general, we have actually seen in this particular case a scaling up of the various, say, parts in the workflow for this typical data assessments, or these assessments, and so both affecting the procurement, the processing, the validation, but also the awareness of these products in the various phases of the post-disaster sequence. And really the purpose of our lessons learned is to try to grab this experience, describe it in such a way that we can use it in future contexts. Say following our analysis work and presentation of the results, which actually are integrated in what is called the post-disaster needs assessment, which is a joint exercise between the UN, the World Bank, and the European Commission to come up with this methodology to produce numbers that are actually used were actually used also, for instance, in the New York Donor Conference at the end of March. What we are trying now to do specifically for this geospatial exercise is to come up with what we call standard operating procedures to describe the workflow in a systematic way and make it available so that it can be used as a guideline. A first meeting of this was organized by UNOSAT at their premises in Geneva, and they were actually putting the people together that were doing the technical analysis in the various stages and try to come up with the key technical issues. A second workshop was organized by ourselves in Italy, and we are now working on this, the outline of this SOP. And of course today we have another opportunity to present results and discuss issues that are maybe broader than just the geospatial analysis, how this integrates into risk preparedness, but also into future activities. So I've split up just the lessons learned part in the data and in the effort. We've seen this very highly detailed information becoming available. So we're talking about 15 centimeter aerial imagery. And at the same time, we also had satellite data, which is our usual source of information after these cases. And in fact, what we discovered in our analysis was that we get significant improvement. So this spatial detail is very crucial in this particular case, especially again because Haiti has a specific kind of urban structure that is small structured and requires this additional detail. There's also other aerial imagery that looks not just vertical but also from the side. I'll show you some examples just after this one. And again, there's additional information that you can derive from this imagery that is, brings additional value. Is also, of course, reflecting on the way how you should process this information. So it has, a feedback into the methodology and the workload. And again, this aspect of ground survey data, how essential it is to actually validate your exercise, but also to help in the modeling efforts that we did in trying to get out the relative distributions of especially the lower damage classes where there's some difficulty to derive that information from satellite or airborne imagery. This is just another example. This is a post-disaster, so this is after the event. It's the satellite image, the satellite version of about 50 centimeters spatial detail. This is one of those areas that was also shown before. This typical, very dense, self-constructed houses on steep areas that are very prone to an earthquake impact. And this is the same image in the airborne. So you see a very clear an upscaling of the spatial detail that you see, and therefore the kind of information that you can derive that is relevant for our model, which is floor space, which is damage class, which is a number of stories, etc. So the more the better the detail, the more useful this information becomes. Similar for this, so the difference between a vertical perspective and an oblique perspective. So this is a building that, if you look at this in the traditional vertical view, you would not classify this as damaged. But if you in fact look from the side, you see this what is called a soft story collapse effect. So the lower story of this building has actually collapsed. The building has come down almost, say, parallel to the its normal position. But of course, this is a case which is actually a kind of a total loss. These kind of buildings have to be rebuilt, and there are many of these. In fact, surprisingly often in cases where you would classify the building as a modern construction. Ground data. So this is just an example of. So these are the points that were collected together with our colleagues at the CNIS, the Haitian Central Center for National Information, Geospatial Information. They've been very actively supporting us, even though both their premises but also their staff was heavily affected by the earthquake. And again, this is ground photography, some of it again showing these particular effects that help us better define the damage classes, getting feedback into the image analysis, and allowing us to estimate where our method is maybe less precise or is working well. Similar activities done by other people using novel methods to, for instance, they had a mobile system, a multi-camera system on the roof, a bit like street view, rapidly deployed after the earthquake, getting very valuable information that is also very easy to integrate in public solutions, simple solutions that allow you to enumerate damage effects quickly and extensively. This is, for instance, covering most of Port-au-Prince and the areas outside of it. For the efforts, we have, of course, realized that in this case where we have spontaneously started to collaborate without an official framework, there are a number of things that you have to resolve there, and there's some duplication. So what we would really try to aim at with our standard operating procedure now is to get a common view on division of work, how we distribute tasks, what tasks can be split out, put in parallel tracks, common methodologies, issues of quality control that we think are very important, but also maybe elements of how do we rapidly share. I mean, the experience, for instance, from Ron's team in doing things in a crowd environment. So all these elements are essential need to be reviewed and detailed. Lots of that was maybe the unfortunate situation also in Haiti, that many of the layers that you would want to have to start your analysis were unfortunately not available. So all the data, all the information had to be extracted post-event. What you would like to have in these cases, of course, to have essential layers that you can maybe that you have available through open means, things like urban structure, building characteristics, all the exposure information that you would like to integrate in your sampling approach, in your statistical analysis, and again to help decide on how you perform this analysis, and what methods do you use, and what resources do you integrate. The involvement of national actors is essential. Having such a capacity, having access to essential data, but of course also having the local knowledge to help you in structuring, sampling, and getting you very early feedback. And then, in general, for the say this geospatial community, there's post Haiti has been quite a bit of discussion on how we should work on the distribution of this information, what is essential to different players, different users at the various stages in the post-disaster phase. And that's an ongoing discussion that is also integrated in this approach. What do we expect as outputs? Is this what the standard operating procedures for this particular exercise? We are now working on the initial draft. It will have additional technical annexes that will detail more specific things, a bit more, the things that are a bit more, say, dynamic, more specific to either data users or specific events. And with this first draft, we hope to actually run tests where we can show that the proposed workflow and then is actually working and essential and actually optimizes the whole analysis setup. At the same time, we're talking with our partners to look at structural measures to support the data provision in a similar way as it was done in Haiti. And then again, addressing both the risk preparedness, so can we actually have the information available beforehand in the say what we call the hotspot areas, so the areas most prone to risk, but also of course in post-disaster context. And a number of these elements are of course also finding their way in scientific publications. That's it. Thank you very much.
Thank you very much, Guido. Sergio, if you want to come up. And we have lots of questions here already, so the pressure is on Sergio to get us through quickly so we have time to address all these interesting questions. Thank you.
Okay, thank you very much. We will have Alix Roumagnac, Jean-Pierre Asté, and Narcisse Aibo addressing you under specific subjects, but we have Javier Saborio in the hall, who is our hidden hero, and without him we could never have done what we had in terms of the geographical information systems. We have two members of the team that could not make it here to Washington, Mathilde Marcelot and Jean-Michel Milcé, which I would like to be clear that we thank very much for the support. This is the old-fashioned modified Mercalli intensity map of the earthquake that we built on the old-fashioned, just making interviews and interpreting newscast media. And then we came to the conclusion that we had intensities up to 10 in some areas. Objects were thrown in the air, figuratively. There are three evidences of that. And then in this zoom, we have the metropolitan area of Port-au-Prince and the areas affected by liquefaction and landslides close by, and then it is very interesting to see that intensities 9 and 10 occurred where most damage was made, and perhaps this is a side effect due to the soft soils that prevail in that area of Port-au-Prince. So we have this kind of images. This is just before the earthquake, picture taken December the 12th, and this is after the earthquake. Fortunately, the same spots were available. I took the two pictures, we were lucky. And then we have seen the type of damage that is typical, and let me warn you, we did not see anything new. We see more, but the typical damage that we have seen in Port-au-Prince is the typical damage that we have seen almost in every earthquake in Latin America. The same mistakes of design, construction, the quality of the materials, short columns, shearing, torsions. I mean, just name it and they are there. So, in my opinion, the lessons learned is just common sense in design and construction, and that will save lives and damage in the future. This is the PDNA's estimate for the economic loss. Virtually in damage and losses amounting to nearly $8 billion, requiring $11 billion for an improved reconstruction of Haiti. And then we tried to take all this into account, every piece of information and data we had, and the thing was to put it available for working. For example, we have this very well done geological map, but we did not have it in digital version, so we had to handle the way to translate it from paper to digital. And then we need to audit different targets to have, I mean, the decision makers trying to understand our products, and this is not always an easy task, but we at the same time have the population that requires information. So we're trying to translate all that into ways that are specifically aimed and in Creole, in French, in Spanish, because the Dominican Republic is also very concerned about what happened there, and of course in English for the international community. So we addressed, we will have a final version of the detailed report for the scientific and engineering community, and we encourage all our predecessors in using this podium to write in French as well, because if the documents remain in English, they will not be available for only the international community, and the Haitians require also that information. So translations to French will be greatly appreciated. So the orientation of our work came into the first place to the point of departure, but this is not the point of arrival. We're just starting our job because all the work we have done requires review, validation, and improvement. And we know the limitations scientifically and technically of our work. But we believe that they are very useful for the short term, focusing on the imminent natural hazards that will occur between the rest of 2010 and 2011. So we prepare these natural hazard scenarios as tools with text to the level of complexity and terminology and the composition required for different target audiences, with the recommendations for risk management and mainstream for risk management as well, in terms of risk reduction, prevention and mitigation, and emergency and disaster management. So we took this information that came also as fixed images, and then we translated it to make them useful for our geographical information systems, such as these intensity maps. And then we prepare the maps that will be addressing, for example, the different types of natural hazards, in this case using geomorphology and geology and VS30 to produce liquefaction hazards, because there is no geotechnical information available for Haiti. And now I leave Narcisse Zaibo to address you on tsunami and coastal hazards.
Thank you, Sergio. So my name is Narcisse Zaibo from University of Guadeloupe in Les Antilles. And Our first reflex in our tsunami community after the Haiti event was, did this earthquake produce tsunami? And when we look on the historical tsunami database of Haiti, you have more than 10 events. And among these events, you have two deadly tsunamis, one in 1842, which produced more than 300 fatalities, and recently in 1946, about 2,000 fatalities in the Dominican Republic. So here we have the localization of the seismic tsunami and the distribution of the different run-up around the island. So we run to try to make the numerical modeling of these events, and just to characterize this, and just after that, a tsunami team with Haitian scientists, with specialists from Georgia Tech University, made a tsunami field survey of these events, and they reported 3 deaths in Port-au-Prince due to tsunami, and run-up of about 3 meters in Port-au-Prince also. And up to date, we continue to receive a lot of testimonies that confirm that this earthquake produced a significant tsunami. So, in order to reduce the future impact of tsunami in this region, so we have to use a kind of troika, which is composed by mitigation, warning, assessment. And what we are now doing in our NatArts project in Haiti is to, through a lot of workshops, to increase the awareness and the understanding of tsunami risk in Haiti. This part is in the hand of the intergovernmental coordination group of Caribbean. So it is necessary to encourage Haiti to take its place in this coordination group, and to maybe to have through this coordination group real-time and seismic data. What I'm now doing now is a numerical modeling of different scenarios of tsunami in Haiti, and I will show you briefly some our first results. This is a numerical modeling of a tsunami. The source is in the area on a kilo fault, and we are now the distribution of the run-up along the coast of Haiti with 3 meters in Port-au-Prince, 2 meters in Gonaive, etc., etc. But the challenge now is to play with a different segment around Haiti, and to analyze the answers of this different earthquake in terms of tsunami inundation along the coast of Haiti. It's a huge work, and we have started this, and with playing with this different segment in terms of earthquake. We can focus on this is Le Cap in the north of Haiti, and to analyze the distribution of the run-up in this region. And this is our first result. This is the potential inundation map in Le Cap from different segments in the north of the subduction zone. This is from the south segment. You have a significant 8 of tsunami in this region. So this is what we are now doing. The result in Gonaive is a superposition of the real map with this inundation zone, and to see the weakness of this region in terms of tsunami. The same in Port-au-Prince. This is Port-au-Prince, yes, and you can see the different districts of Port-au-Prince, okay. And parallelly, we have also made the numerical simulation of the wave induced by cyclone in this region. This is the historical database of cyclone in this region. And by analyzing this historical database, we have seen that the more dangerous cyclone in terms of storm surge are those who have specific trajectory between Haiti and Jamaica. So we have made numerical simulation of this earthquake like the cyclone Faye in 2008, which entered between Haiti and Jamaica. So our numerical simulation saw a significant aid in the Bay of Haiti. So this is a database of wind speed of a cyclone within this region. So the perspective of our work now is to strengthen the public the awareness and the understanding of inundation hazard to make a synthetic catalog of tsunami and storm surge in Haiti, and also in the goal to build the vulnerability map of inundation threats in Haiti. So thank you very much. Okay.
Concerning hydrologic and climate hazards, Haiti is concerned by big risk. First, land degradation and deforestation and climate fluctuation make some drought in Haiti region, and this drought is in correlation with flood vulnerability. In another way, Haiti is affected by three kinds of flood origin: convective stored system, tropical wave, and also a storm, hurricane, generate a lot of events in the last years. Haiti, moreover, is affected by aggravating flooding factors. There is a map of Port-au-Prince area. You can see on this map the very closed valley, step slot catchment area, who aggrave flood problem. You can see on this map that we try, in the lack of data, to realize a flood hazard area with three levels: frequent area in blue, rare, and exceptional. We can see that the problem is a large and dense urban expansion in flood area, like here in Gonaïve, and you have the principal city of Haiti is constructed in flood area. So, with the cooperation of CNIGS, we can realize a national flood hazard map. We can resume the diagnosis of hazard diagnosis of flood in Haiti, that Haiti is concerned by a very large flood risk, high intensity hydrometeor hazards, flood aggravating factors, and vulnerability was increased by the earthquake. The inadequate knowledge of hazard and vulnerability and the capacity of response is decreased after the seism. So we recommend for managing hydro hazard a lot of action. Improvement of knowledge and hazard and vulnerability, development of a strategy in risk communication, risk reduction action plan, and improvement of the early warning system in risk management. But the first part of this action is here in work. Today, the Programme National of Alert Precoce, with cooperation and DPC, relies communal alert and evacuation plan in the principal city of the country. There is warning procedure, emergency chart, hazard levels, and crisis protocol. There's also action map, very operational action map, with answer when, how, who, where must take decision, with a very operational action, some installation of a siren, action to be deployed, area and surveillance points, shelter to be built, and also. In the same time, the Programme National of Alert Precoce install an early warning system. In parallel, the meteorological services is improve its method and tools. So we would like to be optimistic, and why not tomorrow an early warning system operational in Haiti who can decrease the impact of the flood system, and why not in the very short term a Wikipredict alarm system in Haiti.
Our maps today, no, I don't need. Our maps today are only approximations without or with a limited operational value. All the steps of the threat evaluation needs data and additional processing, but of different nature. Physical, meteorological, hydrological, monitoring of seismic events and ground acceleration, active faults mapping, and finally geotechnical. Within this part of Port-au-Prince, we used some of the aerial post-earthquake data produced by international organizations and specifically LIDAR digital elevation models and corresponding orthophotos. But they still remain very heavy to use, and we had to spend a lot of efforts to reduce size, translate formats, or change spatial referencing of available files. Here you can appreciate the difference of resolution between previous 90 meters DTM and the 10-meter one from LIDAR. But we also implemented modern, economic, and powerful processing of 3D data acquisition on slope sectors, starting from photographs carried out with ordinary cameras. We created anaglyph scenes and, most importantly, solid 3D images, which made it possible to detect dangerous zones and to acquire at low cost three-dimensional data for the appreciation of slope stability. It should be too time-consuming to show you all this here, but we remain at your disposal to show them outside the room. Now, it will be dangerous. No, sorry, I made a mistake. About vulnerability, the concept has to be taken into account to help decision makers for their choice in terms of land use planning. Our previous work is a contribution to this evaluation. I hope it will be used to process. It will be useful for processes like CAPRA and diffused via GeoNode. Our specific treatments make possible a detailed identification of elements at risk and evaluation of vulnerability. Like that. Now, it will be very dangerous to avoid the materialization of a project to undertake a local study for hazard exposure and economic loss evaluation, or to undertake only at the last moment a geotechnical study. We are perfectly conscious that in the current situation we have neither nor means and no time to organize in the short term this data acquisition for the whole national territory. In my opinion, we need large and permanent efforts to support the emergence of a national entity in charge of this collection, avoiding the dispersion of efforts in the various ministries. But it is necessary to make sure that the entity in charge of this collection will be obliged to put the collected data immediately and gracefully at the disposition of all actors who need them, from main public or private investor to smallest town authorities. It's particularly important to avoid that such an entity assumes the power to market the collected data, as that occurs in most countries. Today, it's possible with open source systems to vulgarize access to basic and specifically georeferenced database of public interest, and so to favorize bottom-up transfer of information. All that will take time, but it's impossible to accelerate the process through pilot action. If the launching of some of these actions is slowed down by the lack of organization of the ministry concerned at the national level, it is undoubtedly possible to prove their feasibility with sectorial actors like DPC or SIAT, or local actors, municipality of Port-au-Prince and commune of average importance. And finally, I would suggest two of these programs. The first one is a learning on the job training project for territorial hazards and resources analysis for 5 middle-sized towns. It will be achieved within 1 year. And the second one will be an hydrogeotechnical data management system for landslide prevention and construction control on Port-au-Prince hill slopes.
I'm sorry, we respect our time. We finish with some debris flow torrential maps that are available. This is a hazard that has to be reckoned with in Haiti. And then we are in the very short term ready to model what is going on in terms of rainfall and floods that are already occurring. El Niño has dissipated, but it has increased the intensity and number of cyclones. There will be large volumes of rainfall also correlated to tropical waves, polar frost, and local convective systems, and of course the other pending hazards, seismicity, landslides, torrential debris flow, tsunami, drought, El Niño again, and the only solution is an integral risk management. So these products are valid only on the short term. They must be validated and updated continuously. We need fresh data and ground truthing. We need the continuity and sustainability of the effort. And effective use of this information should be assured in order to assist decision-making in public and private sectors and the long-term risk management, land use planning, financial protection. So we want Haiti to go from this kind of landscape to whatever we know about Haiti better. We need a better Haiti from now on. We have to have this opportunity to put it back on its feet and forever. And then, as I said yesterday, essentially we know for whom are we working for. We will be ready for the questions and answers session, and merci en pile.
Can I ask Ron and his team, Carol and the team, Sergio, anyone you want to join you? We have about 20 minutes. I'm disadvantaged. I actually forgot my watch today, so. Let me start with a question. Where's Ron? Is Ron up here? Yeah. Question from Twitter for Ron. Says, congrats. Remote sensing was groundbreaking. Could you address how to link what happens on cloud with what happens on the ground?
I'm sorry, what was the question?
I'll skip the congratulations part. It says remote sensing was groundbreaking. Could you address how to link what happens on the cloud in the clouds with what happens on the ground?
Okay. How do I turn this on? Testing 1, 2.
You're on.
Well, I think we learned a lot of very important lessons with the crowdsourcing. I think it only provides you with part of the answer, and this is what we all found out, was that it gives you a very rapid way to use some very, very powerful data to come up with sort of a first level assessment of damage. But what we didn't recognize was there was a lot of stuff that we did not pick up. There's some very special things such as the soft story effects that Guido talked about that were not recognized initially. So I think that this has steered us very much into a direction of trying to integrate other sources or methodologies of looking at damage, especially field data, in a way that it integrates in with the results that we produce. But I thought the whole exercise and just the experience was just phenomenal, and I hope that we can continue this. In fact, the platform and framework that we started, the GeoCAD, is something that we're working with some organizations like EERI and EFIT to make sure that we can continue for future events. But it was a very, very rewarding experience, I think, for everybody.
Thanks, Ron, for taking that question from Twitter. Let me turn to Mary Lou's team. Are there any natural countervailing movements that would oppose or reduce the earthquake-inducing shifts of the plates? And then, I guess relatedly, can we also artificially release the energy as that is accumulated as a preventive measure?
Is this working? The plates are moving. The problem is that they're locked in certain places, and unfortunately one of my slides was missing that showed where the plates are locked in Hispaniola. But it's inevitable that those areas have to catch up eventually, and that's what happens as an earthquake. There really isn't any good way to release that strain. It has to take place through large earthquakes. Eric, do you have anything you want to add to that?
No. Thank you. Yes, please.
I'll just say that we can generate earthquakes. We know how to do that. We can pump fluids in the ground. We could relieve the strain, but the problem is for each level of magnitude increase, it's a factor of 30 of energy release. So if we wanted to release a potential magnitude 7, we would need 900 magnitude 5s. We would need 3,000 magnitude 4s, and when we generated those small ones, we don't know whether or not we would actually have that small earthquake grow to a big earthquake. So I don't think anybody wants us to do that.
Thank you. Question for Sergio's team. This is a slightly long question, but I think quite important, and it's related to capacity building. What are opportunities or entry points for building the capacity of national actors to use and apply the wealth of data, information, knowledge, etc., that's available in both the pre- and post-disaster sense? Recovery certainly offers numerous opportunities for more sustainable rebuilding, but what about proactive capacity building, disaster risk reduction, example in Caracas or Panama City? The availability of all this data and knowledge does not guarantee its usefulness or its application. And this is from Clackside, from START.
Okay, yes, of course, and this we are very well aware of. I mean, the richness of what information we've got now does not guarantee anything, but only the knowledge on the very short term of what happened and on the ways that we should go through. But we are addressing on the possibilities of continuing learning on the job first as a short-term measure. But of course, science and engineering must go on, and we have to aim on the long term. It is not possible on the short term to put Haiti in a position of a developed country in terms of knowledge. This is not possible. And then we will have to be patient, and then we will have to address this as a strategy more than as a plan, meaning that we have to start, but the end is not on sight yet. And the efforts and the challenges are strong, and it will mostly depend not only on the willing that we as international community could give to Haiti, but also on the way Haiti will accept or not our propositions.
Thank you. Question for Eric Calais. I have a question for you, so why don't, it's kind of related.
I wanted to add a few
Sure.
words on this. I think Sergio is right, and it's the key to all this in the long term is really about training the next generation, and we have to start now. Even though it's long term, if we don't start it now, it's not going to happen. There are universities in Haiti, there are good students in Haiti that are willing to engage in better understanding how to deal with natural hazards. We need to tap into this pool. We need to have big education programs and training programs at all levels starting as soon as possible.
It's a good time to ask the question for you. It says, I note and commend you for the recommendation that future efforts to rebuild Haiti must also build the HR capacity, that is, train the future Haitian scientists. My question is, whether you know of any specific efforts, or will there be any specific effort made to include existing Caribbean educational and research institutions in this effort? For example, the University of Guadeloupe, the University of Puerto Rico, or the University of the West Indies.
Well, I'm not sure what efforts are going on at the regional scale right now, but I know that there are a lot of academic institutions in different countries in the U.S. and also in France and other countries that are coming up with plans to do just that. I guess there's a need to integrate all this in a well-coordinated framework, which is a little bit of a problem because there are lots of initiatives, there's lots of input going into Haiti, and I don't think that anyone has a clear understanding of the whole big picture. I think that's something we need to be concerned about. But there are initiatives. That's a good part of it.
Thanks, Eric. All right, I'm going to take two more questions from here, and I want to assure everyone that even if we didn't get to your question, it will be answered online. Okay. Question for Mary Lou's team. What are the erosion rates at the surface above the reverse fault that ruptured? Please compare to the rest of Hispaniola. Oh, is that Sergio? No? No? Does anyone know? No way to know. Okay.
I mean, there are ways to know, but we don't have the data.
We don't have the data. Okay. Ron, to what extent, I got to take my glasses off. To what extent the Haiti damage assessment work, state of the art, is used to provide better insights or hints about the setting of key variables and or adjusting the EMS 98 methodology, especially as far as damage matrix vulnerability functions are concerned?
You know, I must have a problem hearing. Can you repeat that again?
Sure. Might be easier for me to shout across here. To what extent the Haiti damage assessment work, which is quite state-of-the-art, is used to provide better insights or hints about the setting of key variables and or adjusting the EMS 98 methodology, especially as far as damage matrix vulnerability functions are concerned?
Okay. You know, I think that, in fact, I think the whole experience uncovered, I think, some very important insights into the way we do loss estimation. For example, it's very important for us to decide very early on a common damage scale. In fact, you know, we had started with different scales, and I think that in order to combine and integrate independent assessments, you know, we all have to start with the same sort of scale. And I think very quickly we agreed that the scale that we were using was the best one to start with. However, I think given what we saw and given how we were using the data, there might be ways that you would actually revise and modify the damage scale that we were using in order to incorporate remotely sensed data. Because there are a lot of things that you can't see, and there may be better ways to better define some of the artifacts and some of the damage that we were seeing, and that's one of the things that we've been discussing collectively. Should we be revising the damage scale to be more reflective of the sort of data that we would actually be using? Also, you know, I wanted to come back to one of the other points where the studies that we've been doing, I think, are just really the beginning. We need to look at, you know, the long term and figure out how all the data that we've been creating, the imagery, the looking at land use, cadastral information, how all this information really can be built into a longer term process where we can begin looking at things like better hazard maps, loss reduction measures, opportunities to rebuild in ways that we don't end up in the same sort of situation. And so, you know, we need to understand the workflow. We need to understand what the opportunities are. We need to know what the resources are. And I think really look long term in terms of, you know, rebuilding Haiti. Guido, do you have?
Yeah, maybe with respect to the first issue is that we have very much focused on the physical damage in this financial sense, so trying to come up with this number, and have not really had the opportunity yet to look at all these structural elements. There's a lot of, collateral data still missing try to explain what we see in the grading sense. So I think this would require a combination of other data that is already available. There's lots of earthquake engineering surveys being done. So but what is, I think, very interesting is that we put the data available to anybody who wants to do this in-depth analysis and feedback into grading systems, remote sensing experience. So it's there, and there's a lot of information that can be extracted from that by combining it with further expertise. And so that's, I mean, that's also a bit the limit of our scope is maybe very much the remote sensing side, but I think this link into the engineering community is actually a huge opportunity.
Very good point. Thanks, Guido. Unless our panelists have any specific closing points, yeah? I'd like us to thank them all very much, not only for the wealth of information they've shared with us, but for their long-term commitment to Haiti. Thank you very much. I'd also like to thank all of you for attending the session, Haiti, January 12th and beyond, and wish you very productive meetings for the rest of the day. Thank you.